Our next speaker today is Greg Chance from the University of Bristol. He is a senior research associate there, working in the Trustworthy Systems Laboratory at the University of Bristol. His current research interests are simulation-based verification, exploring trustworthiness in autonomous systems and how they can be verified. He's currently working on EPSRC TAS functionality node project with the Bristol Robotics Lab, working with swarm robots, soft robots, and UAVs. Hi, Greg.
Thanks, Mike.
Hi. Go ahead, Greg.
Hi. Can you hear me okay? Great. Right. Yep. So, hi, everyone. I'm Greg Chance. Working at University of Bristol in the Trustworthy Systems Lab with Kirsten Eder. And just wanted to talk to you about some different tools and techniques that we've been looking at in order to look at autonomous test case generation. So we were looking at the challenges of autonomous vehicle testing and how we can sort of understand failures, how we can detect bugs in the system. And although I agree completely with Peter in the sense that runtime verification is going to be absolutely necessary, I think there is a large amount of work that can be done beforehand to get you into that operational state. And so that's what we're trying to do here. We're trying to gain confidence in the correctness of the system. And we'd advocate the use of simulation to allow us to do that, giving us full control of the environment, increasing the frequency of rare events. And this can be used as sort of providing evidence to regulators. How can we effectively generate tests? Can it be automated? And can we still get interesting and useful tests if that is automated? And then how much testing is sufficient for getting some kind of level of confidence? Some researchers have quoted figures of hundreds of millions of miles for road testing, and Waymo have done billions of miles of simulation. But we're wondering whether we can sort of be more targeted than this. And we propose this use of agency-directed test generation. And we wanted to know whether this method could outperform, say, a random method, and at what cost we could achieve that. So as I said, verification here, as you all know, looking at the correctness of a system relative to its requirements and making sure it doesn't differ from its intended function. So we developed a test bench alongside TestSolve, and we were looking at providing a stimulus to the design under verification, in this case, an automated vehicle. And if this is automated, this can be a much more efficient process. So what do you do then when you have your test bench, where you need to generate some tests to use that? And this can be challenging to generate valid tests that are realistic and interesting. And what I mean by interesting here is that it's not just giving you miles and miles of open road endlessly. So we decided to use this idea of agency to verify the device under verification, the autonomous vehicle in this case. So what we wanted to use was this idea of agents that could sense the environment. These would be software agents in the simulation, and they would be rewarded if they met certain verification goals. So the agents can interact and coordinate with each other in order to better reach those goals. And those goals in this case, as you can see on the right-hand side of the test bench, is a rule, external rule of or group of assertions. Those might be traffic rules, social norms, and we can apply coverage to those and direct those agents towards getting that assertion coverage. But equally, that could be requirement coverage driven, or even any other sort of coverage you'd like to apply. So our research questions were really, can this agency-directed technique beat a random test generation? And can they generate good test cases? And what I mean by a good test case? Well, a test case optimally should be effective at detecting failures. It should be efficient in tests to reach the verification goal. It should be economic in its terms of its resource utilization. It should be robust to changes in the software, And I've added another one on here in terms of being realistic representation of how the system will be sort of ultimately deployed. And so my metrics for success in terms of my agents would be how accurate the test can be generated per a number of episodes, and that would be an indication of effectiveness. For efficiency, how many tests, useful tests are generated per simulation cycle. For economy, we looked at CPU time for agent execution and the number of lines of code. And in terms of robustness, we could apply the agents to different alternative environments than the ones that they were initially sort of designed to work in. And then in terms of realism, how does this compare to how we observe traffic behavior in reality? So we developed this test environment. We started with a grid world, and you can see the images on the right. We had a simple system of a autonomous vehicle driving from left to right. And in front of those are two areas. The first is a stopping distance where you would get an unavoidable collision. But beyond that, there was this precondition zone, this area where if there was a pedestrian sort of found in the path of the autonomous vehicle, the vehicle had the time and ability to stop and avoid that collision. So what we're really interested in here is pedestrian agents being found in this precondition zone. And we chose this because this is based on the pedestrian safety tests, so the Euro NCAP, vulnerable road user assessment. In this case, we don't have an AI where the vehicle moves at a fixed speed, and we're doing repeated tests and looking at how many pedestrian agents were found in this precondition zone. So we repeated this experiment for multiple different agent types. We had a couple of random agents. We have a Gaussian agent, which just moved in a random direction in each simulation tick. Then we had a constrained pedestrian, which would walk along the pavement, but then randomly cross the road. We then had a proximity agent, which would cross the road when a vehicle was in a certain distance, and then an elected sort of group of agents, which is similar to proximity. So you'd have a group of agents, but only one would elect to cross the road at a single time. So some results. You can see on the graph here, we've got number of agents plotted against the accuracy. So this is the effectiveness of the test generation. So for n number of tests, we can see that the proximity and election agent give us about 50% accuracy. So 50% of those test returns for a single agent are useful tests. And we can see this is about 3 times higher than a random technique. We can also see that when you have lots of agents, it's very easy to get very high accuracy, but lots of agents is a high use of resources. And we can also note that a single agency-directed pedestrian is equivalent to 3 or 4 random agents. So we wanted an idea of kind of realism. We didn't want just pedestrians walking in the road and triggering the precondition. So we decided to give the pedestrian agents a score. And so the less time the agent spent in the road, the higher the score. And so you can see here in the graph, we have agent score as a function of number of agents, and the random agents perform, well, they achieve quite a low score. You can see the maximum attainable score there in green. And the agency directed do a bit better because they're sort of designed not to spend a long time in the road. In terms of economy, so we're interested. So here we were measuring the action execution time of the agent in the program, and we noticed that random is very fast, as expected. The agent is less economic. It's about 4 times slower than the random techniques. So the agency is taking more CPU resources to achieve those test cases. However, if we look at test generation time, so how long does it take to generate a useful test case based on simulation ticks, the agency is quicker. It's about 27% quicker on average. And this is because, and this is good because Fewer ticks means that if your simulation is expensive to run on a simulation tick basis, this would be more beneficial for you. So as a summary of those results, we can see this is a summary of 3 pedestrians here. So we've got our 3 pedestrians of the various classes here. And we can note that the random and constrained have sort of a low number of lines of code. We can see going from constrained to sort of proximity, it's only a few more lines of code, but we do jump up in terms of the accuracy. The CPU time is higher going from constrained to proximity, but we get a much higher score, and we can also see that the number of sort of simulation ticks is also has dropped significantly. For the election agent, there was a lot more sort of lines of code. The accuracy wasn't particularly, it wasn't as high as the proximity. But we do note that there was an increase in the score, so we saw less pedestrians in the road. And this is a sort of indication that you might be able to use this as a tuning method if you wanted to optimize your test case generation. So we published this at the AI test a few years ago, and there's a link here if you want to take a look at that paper. We've made some additional improvements to the agents to try and make them more effective and robust. One of those techniques was to use a machine learning or a reinforcement learning technique based on approximate Q-learning. So we gave the agents in this case a functional approximation of the environment. For example, we would generate a feature saying that the autonomous vehicle is moving away from us or towards us, and so on. And what we found is that the agents learned quite quickly from these features. And we can see on the graph on the top right here, we have our existing agents and the Q agent, which is the orange line at the top. And we can see now we're sort of 5 times more accurate than a random-based technique. The plot in the lower right-hand corner just shows you the development over a number of episodes of the different agents. We can see that the Q-learning agent holds a high accuracy and learns quite quickly. So the table in the lower left, gives a brief summary of the different agent types. And we can see that the Q agent does achieve the highest accuracy, but also has a significantly higher CPU and sort of execution time. But this is still better in terms of simulation ticks than the random techniques. So an additional improvement we wanted to make was in the placement of the agents. So initially for the previous tests, the agents were randomly spawned into the map. What we wanted to do now was improve the accuracy of the test generation by learning good start locations. So we wanted to find a function that maximized the reward of the agent based on the verification goals. And so we used some energy-based modeling techniques to do this. And so we would have the agents randomly spawn, but over time they would learn good spawn locations and exploit that. And this improved the accuracy. In the top right, you can see a graph of the energy field as it developed over time. And this corresponds to the layout of the road below it. So we can see that, let me just move this a second. So we can see in the table in the bottom right-hand corner that we do get an improvement in accuracy in some of the agent types, but there is a penalty in terms of CPU time. So again, it might be something else that could be useful in terms of tuning the test generation techniques. One future improvement on this energy-based modeling might be to estimate the energy field based on the environment. For example, we could look at position of roads and pavements, crossings, and estimate good starting locations based on that map information. Some other improvements we did to our environment were to look at sort of going from a grid world to a more sort of continuous space. So we moved away from that and we borrowed some technology from OpenAI Gym and we developed what we call CAVGym. So this is more of a dynamic environment where we can, you can see in the top right picture, we have vehicles moving, and you can see the braking zones and precondition zones that precede the vehicles moving dynamically relative to their speed and acceleration. You can also see red lines which indicate occluded areas, because we were interested in having sequences of tests that were derived from an agent being occluded, say, from moving behind a tree or another vehicle. And with this technique, we can build up more interesting test cases based on, say, for example, a pedestrian moving between two parked vehicles on the side of the road. We can also use this platform to take on more capable sort of machine learning techniques, and even look at sort of a game theoretic approach where we have all the actors in the simulation as a player against the autonomous vehicle, and then they are tasked to play a game, in a sense, to try and achieve the verification goal. You can take a look at our code on our TSL UOB GitHub page, and it's called CAVGym. And just to demonstrate what we can do with this, so in the bottom picture, we've actually put the Q-learning functionality into a vehicle, and we've given that vehicle the penalty of not colliding with one of the pedestrians, or not getting a pedestrian in the precondition zone. So we've kind of turned this problem around now. And you can see within, this was trained sort of like within a few hours. And you can see without any direct coding, this is avoiding those pedestrians by slowing down, allowing them to cross, and then speeding up again. And then finally, we wanted to port these trained agents into the full 3D simulation environment that we use for testing. So we use Unreal Engine 4 and Scala now. And we successfully ported these agents that were trained in the 2D environment and moved them into Scala. The animation is not working. I'm just going to go out to full screen so you can see them. Hopefully you can see that. Just wait for that to go full screen. Okay, so in the top video, you can see pedestrians walking along the pavement, and then we have a proximity agent on the top pavement, and as he gets into a certain radius of the yellow car, he moves into the road to cross. So we like this setup because you can use the 2D environment to develop your agent-based test generation technique. You can optimize it, you can train faster, and then port it into the full 3D simulator, which would be more expensive to train in initially. And we also sort of prove this verification agents against a real pod controller as part of the Capri project, which you can see moving in the bottom right-hand corner there. Thank you for listening. Hopefully you've learned about what good test cases should be, how software agents can beat random test generation for a minor sort of extra resources, and how Q-learning and energy-based modeling may help you to improve your test generation performance. Thank you very much.
Thank you, Greg.